So I'm going to demonstrate how to conduct simple linear regression using SPSS. I'm using the album sales data that I used within the main lecture. So I've got 4 variables and they're all scale variables. So initially what I'll do is, with simple regression, I want to build a model that will somehow help us to predict sales based upon one of these 3 variables, one of these 3 other variables. Okay, so I've got a legacy dialogues, scatter dot. I'm going to do a matrix scatter. I'm going to define it. First of all, I'll have my album sales start as my first variable in there. Then I'll put the other variables in, just in the order they appear. Simply press OK. And we can see that this row refers to the album sales in thousands. Okay, so if I scroll along this row, this is my first variable that was in the data. Okay, and we can see that that is not very strongly correlated. There is some correlation there, but I won't say it's terribly strong. Okay, similarly for this variable. So this variable here looks like it's the strongest variable. So it's my second variable that I entered into the data. If you can't see it, because sometimes when you have many variables here, these matrix scatter plots look a mess. And what you can simply do is just go back to your graphs, go back to the scatter, the matrix scatter, the define, and you'll see that that's the variable on the first row. That's your first variable, that's your second variable. So it looks like number of plays on the radio is the most strongly correlated variable to predict album sales. So what I'll do then is I'll conduct my regression analysis, linear regression. My dependent variable is album sales. My independent variable is number of plays on the radio. Okay, I'll default to having enter in there. Okay, I'm not going to worry too much about any of these apart from on the plots. I'm going to put in my residual plots, and I want on the y-axis the Z residual, and on the x-axis my Z prediction residual. I'll have a histogram and a normal probability plot. Press continue, press OK. It gives out a great deal of output straight away. Our model summary, okay, so it says that the fit is 35.9%. Okay, the ANOVA table, this significance value, which is our p-value, is 0.000, which is less than 5%, so it's significant. What that means is a null hypothesis is that the model isn't contributing. Okay, an alternate hypothesis is that the model is contributing. So here we've got a model works. Okay, so the model works. It's not guaranteed it's the best model or anything, but a linear model does capture some of the information that we require. So then if I move down to the coefficients table, and you'll see in this case both the constant and the number of plays on the radio are both less than 0.5, which tells me that we have significant constant and a significant variable for numbers of plays on the radio. The coefficients are 84.873 and 3.939. Okay, these are effectively the parameters. Okay, the estimates of the parameters. So you could actually calculate 95% confidence levels associated with those, and it is an option within the statistics button that you see within the regression. If I then scroll down and look at my charts, okay, so this is my regression standardized residual. So this is a plot of the errors of the fitted line against the predicted values. and you see that the mean is 2.26 e minus 16, which means 2.26 times 10 to the power minus 16, which is very small, it's almost zero. And the standard deviation is 0.997, which is very close to 1. In other words, this data is following something very close to a standard 0-1 normal distribution. This is also highlighted in this plot, in this PP plot here. Okay, if data follows a normal distribution, it will sit on that identity line, or very close to it, and we can see that most of our data is very close to this line. Okay, indicating that we do indeed have a normal distribution. Furthermore, we must remember that one of the main assumptions that we make is that the errors associated with our plots are normally distributed. Okay, and what that also implies is that when you plot the standardized residuals against the standardized predicted value, you should have a random scatter. And indeed our data does look randomly scattered. Okay, so everything is pointing towards that we've got a reasonable model. And I say reasonable because it's not a brilliant model. Our measure of fit is our R² value for a simple model, okay, and it's only approximately 36% fit. So that's saying that 64% of variation is coming from something else other than the variable number of plays on radio.